defense online, so please forgive us if there will be any hiccups. We'll attempt to proceed in the usual way. That is, we'll start with the presentation open to the general audience and ask everyone to refrain from asking questions unless they concern explanation, a direct explanation on the presentation. And then we'll entertain questions from the general audience for a few minutes, after which we'll excuse the general audience and limit the meeting only to the committee members. Thank you to all the committee members for participating. All right, so Jaime, maybe before you start officially with the presentation, you spend a couple of minutes telling us a few things about yourself, where you're coming from, where you were education, where you educated, and you know, what are the classes that you have taken? Very quickly, please.
All right. Yeah, sure. Thank you. Yes. So very brief background and bit of the last years. I come from Colombia. I studied in the National University of Colombia in Bogota. I had a degree of mechanical engineering, bachelor's degree, and then a master's degree also at the same school. For some time, I've worked with the shipyard of the Colombian Navy. I worked in some research and design with them before joining to the CSM program in 2015. I started in the track of computational science and engineering, but as the time passed, I also joined many classes of math because I really started liking all the rigor of math, both in the applied side of functional analysis, but also some pure math like topology. And that's something that I took from my time in the PhD program. And because of my background in mechanical engineering, I finally chose an application related to elasticity. I think that's a quick overview of my time in the program. Thank you. All right, so do we get started with the talk?
Yeah, let's get started. Let me repeat the request to everyone. Please switch your video off to maximize the bandwidth for Jaime.
Okay, let me.
Thank you.
Por favor, apagar video y micrófonos. All right, so let me just set the timer for me to control the talk. And let's get started. Good afternoon. Thank you so much for being today here at my PhD dissertation defense. My name is Jaime David Mora Paz. I'm going to present to you today my dissertation with the title PolyDPG, a discontinuous Petrov-Galerkin methodology for polytopal meshes with applications to elasticity. I thank the presence of my dissertation committee and thank them for serving for my dissertation. Okay, Dr. Ghattas finally joined. So this is the outline of the talk. After introducing some motivation and background and the goals of the dissertation, I will start with the technical part of the talk. I will explain how PolyDPG works and how it's implemented, and then I will explain some applications in finite elasticity and just give some list of contributions and future directions in the conclusions section. So, introduction. The elastomeric syntactic foam is a composite material. I'm showing here some pictures of the matrix and the aggregate material of this composite material. The matrix is a silicon elastomer, and the aggregate or fillers of this composite are glass microballoons. If you see in the picture on the right, you can see that the diameter of these microballoons are several tens of microns, and the thickness is just a couple of microns. And these are all dispersed in a matrix of silicon, which is a hyperelastic material. These two materials have very different physical properties, but in combination, they present several physical properties that make it useful for applications like conformal coating for electric devices and electronic devices. And in this application, this material is subjected to compressive loads. So there have been some research at Sandia National Laboratories since some years ago, where they have been simulating the compressive deformation of this material and to study the mechanical behavior. And one of the challenges that have been identified in these simulations is that the current finite element methods that they have in place hardly capture all the large deformation that this material is capable of. So in these examples, only 30% of the strain can be captured, while the material can get up to 60% of deformation. And then there's a gap that we would like to help filling, providing another finite element method suitable for this kind of application. So there have been some positive experience in two-dimensional simulations with materials of similar configuration that have been performed with polygonal meshes. And those methods are, for instance, polygonal finite elements and virtual element methods. In both cases, they have outperformed finite element simulations with traditional elements like triangles and quadrilaterals. We have also developed a methodology with the DPG finite element method to work with polytopal meshes. So we think that with versatility of DPG, we can provide a good tool for this kind of problem in 3 dimensions. So the goals of the dissertation are to develop a computational tool or code capable to calculate finite element numerical simulations to boundary value problems in 3D that are discretized with general polyhedral elements. We want to develop mathematical foundations to understand the convergence and the behavior of this kind of method. And we want to demonstrate that the proposed method is applicable to nonlinear elasticity problems like the one that I introduced. So let's see what PolyDPG is. So why have we introduced DPG for polytopes? Well, in the recent decades, there have been numerous applications where the researchers have used polygons and polyhedra as elements of the discretization for a wide range of science and engineering applications. And triggered by that, many diverse methods have been formulated. For instance, mimetic finite differences, virtual element methods, hybrid high order methods, several types of discontinuous Galerkin and finite volumes, and so on. That means that this is a very active field. And with DPG, we also entered this field because this methodology guarantees discrete stability. We can work with high order discretization. We will provide a Hermitian positive definite matrix even when the functional setting is non-symmetric, which is a very nice property. And the key property is that it's very flexible with respect to variational formulations. And this is key for us because to extend the method to polygonal and polyhedral elements, we will use a special variational formulation. So let's see one model problem where we construct that variational formulation. Consider the Poisson equation for a bounded polyhedral domain, but instead of using the typical second order operator, we will write it as a first order system of equations, and we will add this boundary condition. And using this first order system of equations, we will construct the ultra-weak variational formulation. So in this case, we will have 2 field variables, which are u and sigma, and we will test with functions and apply integration by parts, and we'll take all the derivatives to the test functions. And doing that, we obtained this bilinear form where we have introduced 2 test functions, v and tau, which will live in the sublet spaces h10 and hdiv. But the trial functions will now be in just L2 spaces, so there's no high regularity that we are requiring from our trial space. Moreover, if we want to relax even more the regularity requirements for the test space, for instance, then we can use broken test spaces or product test spaces. That's instead of having a global regularity like these spaces have, we actually only require that regularity to be satisfied in each element of the mesh, but on the global side, we will stay just L2 functions. So that's how the broken test spaces are, and we're going to use them to test the first order system, integrate by parts, element-wise, and in the process, we will observe that there are two terms that will be somewhat troublesome, because if we want to work with these two field variables, sigma and u, in the space L2, then the traces on the boundary are not well defined. And so instead of using this, which would be wrong, we will have to introduce new unknowns. And those unknowns have to be drawn for the appropriate spaces. Those spaces are subvolume spaces defined on the mesh skeleton. And those spaces are h1 half 0 and h minus 1 half 0. And we will add to our formulation two interface variables, u hat and sigma hat. So now we have a formulation that has four unknowns, two field variables, two interface variables, and a modified bilinear form where we have added this new contribution from the interface variables. But now we are testing our problem with broken test functions. So this is what we call the broken ultra-wide formulation. And that's what we are going to use for our PolyDPG method. But PolyDPG is a version of the DPG finite element methodology, which is the discontinuous Petrov-Galerkin methodology. And I'm going to talk very quickly about how this method is formulated. So we suppose that we are given a variational problem, like the one that we have right here in this line, and that is posed in Hilbert spaces, U, the trial space, V, the test space, and we assume that this problem is well posed in the continuous setting. So now we want to approximate the solution to this problem using certain discrete trial space, possibly made with polynomials, as usual. And with that, we construct the ideal DPG method, which is a reduced formulation from this problem. It's a discrete version where the test functions are drawn from a very special subspace of the test space, V, and that space is constructed with something called a trial to test operator. So with the trial to test operator, we map the trial space, the discrete trial space, to the test space by using the bilinear form and the inverse of the Riesz map. And we have a Riesz map because we are working with Hilbert spaces here, but the inversion of this operator may not be possible for general test spaces. So what we do is we approximate that operator by using a finite dimensional subspace of V instead of the entire V. And now that this is a finite dimensional space, we can construct this Riesz map, we can invert it, and that will give us the practical DPG method, in which we will have this algebraic problem where we will assemble this matrix. This B opt is the near optimal stiffness matrix, and in the process of constructing that, we have to construct the usual stiffness matrix, the matrix G, which is the gram matrix or matrix representation of the Riesz map. And inverting this matrix is not so expensive because this can be done locally. So with broken test spaces, this inversion is performed at the element level. And finally, the assembly of this finite element method is done as in any other method. So let's see how we apply that to PolyDPG. The starting point would be to have a mesh that we are given of polyhedral elements, and we want to find the discrete spaces that we want to work, that we can work with for polyhedral elements. So let's see. We want to work with polynomials. Let's see how to construct conforming spaces for the trial space. So three of the four variables that we have seen in the original formulation are of low regularity. They live in L2 spaces or H minus 1/2. We can construct conforming spaces with discontinuous piecewise polynomial functions without any issue. But this fourth variable, U hat, that lives in this space, for conformity requires the global continuity of the basis functions that we are going to use. And that global continuity will be throughout the entire mesh skeleton. So in 2 dimensions, the mesh skeleton of a polygonal mesh is the union of line segments. And constructing that is possible, and we can prove that that is a conforming method, and we have done a mathematical analysis and a series of numerical experiments in this paper, published in 2018. But in 3D, the mesh skeleton can be the union of polygonal faces and general polygonal faces, where finding conforming globally continuous space in general cannot be done. So we opt for a non-conforming discretization of this variable U hat, and in the end, the discrete space for PolyDPG will have these 4 subspaces where we use polynomials of degree p-1 for UH and sigma h defined on the elements, polynomials of degree p-1 for sigma hat defined on each face of the skeleton, and polynomials of degree p for U hat defined on each face. But we have to satisfy the boundary condition, so this will be 0 on the boundary faces of our domain. So let's see how we implement something like this. So we have developed a code called PolyHP3D, which is a child of the HP3D code developed by Professor Demkowicz and all the collaborators throughout several decades at UT. And this flowchart that I'm showing is very similar to the implementation of most finite element methods. What I want to highlight here is these 2 blocks here, where we have to construct an affine coordinate system for each polyhedral element, because polyhedral elements don't have a master element notion as we do for hexahedra or tetrahedra. So we have to construct certain coordinate system that will be useful to the evaluation of shape functions. And we also have to determine the integration rule for these kind of elements that are non-standard. And the same for the faces where we have general polygonal faces, we have to do something like that as well. The rest of the process is done as many other finite element implementations. So let's see what type of meshes we are supporting. I'm going to show 2 special types of polyhedral meshes, but we can support more general types as well. One of them is Voronoi tessellations. And we are generating Voronoi tessellations with a software called VoroCrust, which has been developed at Sandia National Laboratories by Dr. Mohamed Aveida and many collaborators. One of them is here at the Oden Institute, Professor Bajaj. And this code generates boundary conforming Voronoi tessellations with several important properties in its geometry. So I'm giving here an example of the boundary representation that we have to feed the code with, and this will give us a boundary conforming triangulation of the surface, but in the interior, we will have the Voronoi cells, which are polyhedral cells, convex polyhedral cells that can be of many faces, like we see here. And this is a cut of a mesh that we have generated with the code. So we have cooperated with Dr. Mohamed Aveida in the interaction of VoroCrust with PolyDPG. Now, another type that I have used is agglomerated tetrahedra. This is an idea that has been around for a few years, has been introduced to DG methods, but here we can use it as well. We suppose that we have a body, possibly with several subdomains. What we do is we mesh it with a standard mesh generator for tetrahedra, for instance, and using NetGen. And after having a mesh that is conforming to the interfaces, we use a graph partition and package Metis to group some of those tetrahedra, and we will have very general shapes of polyhedra. And I'm showing here an example where we have a body of 2 subdomains. Here we mesh it with NetGen and showing a code where you can see barely the interface between the 2 subdomains. And then we group these tetrahedra. And I'm showing here how we have some weird shapes where we can see that several triangles or tetrahedra have been put together. Okay, so the other thing that I want to talk about is the construction of the coordinate system to evaluate basis functions. So what we do is we construct an affine coordinate system. This is done for the elements in 3D by choosing 4 non-coplanar points that we can use to construct the affine coordinates and use this transformation between affine coordinates and physical coordinates. And those 4 points are, in our case, 4 different vertices that we have certain criterion to select. And in 2D, for the faces, we have to do something similar. We have to pick 3 different vertices and construct an affine mapping. So after having that affine mapping, we can imagine that we have this unit element that is mapped to the physical space through an affine mapping. And as usual in final elements, what we do is we draw shape functions, or polynomial shape functions defined on the unit element, and we push them forward to the physical element using the Piola transformations of push forward operators that we use typically for the different kind of spaces. So we use that for the trial spaces, and we also use that for the test spaces when we use P enrichment, which is the classical way to enrich functions in DPG. What we do is we pick polynomials of degree P plus delta P, certain enrichment, but the construction is the same as the previous one. But here we have also introduced another type of enrichment. We call it HP enrichment, in which apart from the enrichment in the degree, we also construct a sub-mesh in each polyhedral element. And on that mesh, we will build a final element space that will be conforming to the space that we want. So there are certain advantages and disadvantages of using both of these, but we have computed with both, and we have interesting results for both of them. How we do the integration? So the general way to integrate in a polyhedron would be to use a composite Gaussian quadrature. So we break the element in tetrahedra, and we use the Gaussian quadrature of each of those tetrahedra, and then we sum the integral. But in some cases, we can use something called homogeneous numerical integration. This is an idea that has been around since 1998 and recently has been applied to methods with polyhedra. And the idea is we can transform volume integrals into surface integrals by having homogeneous functions in the integrand. And yeah, those homogeneous functions in our case will be monomials. But what we observe and what the other researchers have observed is a significant reduction in the time that is required to build the biggest matrices in our element computations. We have observed that, and we're very happy that that has helped us in the performance of our method. And the boundary integrals are also performed using 2D composite quadrature. All right, let's see some numerical results for linear problems. First of all, the Poisson equation that I introduced. This is a sample of the type of meshes. This would be a coarse mesh. After several refinements, we have this. We call these structure meshes, and we use here P enrichment for the test space. I'm showing for the 4 unknowns, the solution for the 4 unknowns, and with 4 different polynomial degrees. In all cases, we see expected rates and the convergence. Here we're using relative L2 error as the metric, and here we're using some scaled L2 error phase-wise. Maybe in the future we can use for this sigma hat variable that lives in h minus 1/2 the norms that Thomas Führer has recently presented to us for negative subordinate spaces. Another example of the Poisson equation is done with Voronoi cells, and in this case we use HP enrichment. This is a sample of the mesh. Here, these are the interior elements of this mesh. You can see all the complicated polyhedral cells with many phases, sometimes 40 or 50 phases. And I computed with 4 different polynomial orders. And for all the 4 variables, we can observe the reduction in the error and the convergence. So now let's see another linear problem, linear elasticity. We have this domain, which is kind of a brick that we have cut out a quarter of a sphere. We have a smooth manufactured solutions, and this material is compressible, homogeneous, and isotropic. And what we are going to do is compare the results using conforming DPG with hexahedral elements and with Voronoi cells. So this is one of the sample plots using Voronoi cells. I'm using 3 different meshes. In the coarsest mesh, we can see that the error here, this is the error in one of the displacement components. We have a kind of large error in some region of the domain, but as we refine, that error starts dissipating as expected. And in these plots, the red line corresponds to the Voronoi meshes, and the blue line corresponds to hexahedral elements for p = 2. And in both cases, we observe that the rate is near 2. So the convergence in both cases is as expected. So that's nice that we have observed similar behavior with these complicated polyhedral elements than the one observed for classical parametric hexahedral elements. And the second example for linear elasticity would be this problem with 2 materials. So we have a matrix of a compressible material and a sphere inside of a compressible material. And we have constructed a manufactured solution that guarantees the continuity of the displacement in the traction fields across the interface and that the body load vanishes. So this is the problem setup. And I'm showing here just some sample plots of the one stress component and one displacement component for p = 2. And on this side, I'm showing the results for tetrahedral meshes. And on this side of the mesh of the results with agglomerated tetrahedra. So those polyhedra that we construct by grouping several tetrahedra. And we are happy to observe that in this case, we have the convergence for all the polynomial degrees. Over here, there might have been some conditioning issues. We cannot explain what happened in that past case, but we observe the convergence for this complicated configuration where we have a compressible material next to a compressible material. So very quickly, some of the ideas for the analysis of PolyDPG with non-conforming traces. So the driving idea for the analysis that we have developed is that a discretization of the trace U hat made with discontinuous piecewise polynomials is non-conforming in the space h1/2 as the original variational formulation, but turns out to be conforming if we work with h1/2 minus epsilon. So some small positive epsilon, we perturb the trial space and this becomes conforming. So using this idea, we reformulate the problem, posing our trial and test spaces in fractional subwave spaces. We construct several of these formulations, including the ultra-weak, and we can show in several steps that these formulations are well posed. And combining this well-posedness of the ultra-weak formulation with this lemma, where we find that there is equivalence between the localized fractional subwave norm and the global non-local norm, we can also show that the broken ultra-weak variational formulation is well posed. So after having that well-posedness, we can apply DPG, and in particular the practical DPG discretization. And for this discretization, we have a theorem for stability, where we have found that that the error will be bounded by the best approximation error multiplied by this power of h, which is if epsilon is very small, this will be near 1, but there's a constant depending on epsilon that blows up when epsilon tends to 0, which is something to be expected because at epsilon equals 0, we don't have the conformity to use these methods. And in the paper that we have published just this year, we have much more results in theory and in practice. So now let's jump to the second part, which is the ultra-weak version of formulation for finite elasticity, so the main application that we want to work with. So just to go quickly without reviewing all the concepts of continuum mechanics and finite elasticity, I just want to say that we're going to work with a body that occupies a bounded domain, omega, and that there is a motion map called phi, and that we're going to use a material description of the motion. Here we're going to work with quasi-static problems, so there's no dynamics involved. I want to remind that there's a very important quantity in finite elasticity, which is the deformation gradient, which is the gradient of the motion map, and that it will be an important piece that we have to use for the evaluation of our constitutive laws. So there are several definitions that we could remind, like the elastic body is that for which there exists a response function for the stress, and in particular, we're using the first Petrov-Galerkin stress for our formulations. And that constitutive law, which would be the function k, has to comply with several constraints, for instance, the material framing difference that has this mathematical form. And we can also impose extra properties, for instance, isotropy that has this mathematical form here. And one of the important assumption that we're going to use is that we're working with hyperelastic materials. So a hyperelastic material is that for which there exists a stored energy density function, W, whose derivative with respect to F is precisely the stress response function. So by combining hyperelasticity and material framing difference and isotropy, it can be shown that a constitutive law for the energy can depend only on the singular values of F, which are called the principal stretches of the motion. And I want to define also the elasticity tensor, which is the second derivative of W with respect to F. Okay, so there are additional constraints and properties that this constitutive law can have, and those are related to the behavior of large strain that resembles the intuitive idea that extreme stresses should follow extreme deformations. And there's the coerciveness condition, which is a stronger condition than this second one right here. And there is the polyconvexity condition, which is something that is weaker than the convexity of the constitutive law. But it turns out that it's a very important property to comply because convexity as in itself is a non-physical assumption for the energy function. So instead, we can work with polyconvexity. And the last property that I want to mention is the strong ellipticity that resembles the ellipticity that we have in linear elasticity. Okay, so after taking into account all the first principles and several of the definitions above, we will arrive at the general form of our nonlinear problem. So this general form will consist of a first equation, which is the balance of linear momentum, a second equation, which is the satisfaction of the stress response function by P, which is the first Petrov-Galerkin stress, And then this third equation, where we satisfy the quality of the new variable, which is called d, that is the gradient of the deformation. And here we're going to use d instead of f for the evaluation of k. So replace the argument here, I plus d instead of f, that is equivalent. But it's convenient for computations that we work with d instead of f. And we have appropriate boundary conditions for the problem. And this general form is very commonly presented in a reduced form where there's only the displacement field as the unknown. And in this case, this is what is used for usual computations of final elements and the analysis of the problem. But the problem, the nonlinear problem, can be presented as well as an energy minimization principle. This takes advantage of the existence of an energy density for hyperelastic materials, with which we can construct this total energy functional, and which integrates the energy throughout the body. And the problem is to minimize that energy functional. And the first question is, okay, but do we have a minimizer for this energy functional or not? So John Ball in 1977 have proved that given these properties that I have shown for the stored energy function, and given a non-empty set of admissible motions, there exists always a minimizer for the total energy functional. So these are weak assumptions that we are imposing on our model, and we find that there is always a minimizer for this problem. But there's nothing said about the uniqueness or the smoothness of the solution. To get to that, we will require many more assumptions. But one of the important things that I want to take from here is that the set of admissible motions give us that the motion map, or similarly the displacement field, belongs to the Sobolev space W1P, where P depends on the coerciveness property of the material. Another approach to tackle the nonlinear problem is to study the local existence of uniqueness. So that means that if we are at an equilibrium point and if we perturb the system a little bit, can we solve the nonlinear problem uniquely? And the answer is yes. This has been developed from the 50s by Stoppelli, and there are many researchers that have reused the results. But one of the important things here is that to achieve this result that gives also uniqueness of the solution, we have to make much stronger assumptions. For instance, high regularity of the constitutive laws and high smoothness of the boundary of our body. And sometimes those are unpleasant assumptions, because in practice we will see many problems that cannot satisfy something like that. But this theorem will give us that the solution will belong to the Sobolev space WSP, and this indices SP has satisfied this relationship. And if we want to set S equals to 1, then P has to be greater than 3 for the three-dimensional case. And we see that that has a similarity with the result that we saw in Ball's theory, that we can work with W1P spaces. All right, so also the second approach is based on the properties of the linearized problem. And the linearized problem is something that we need to construct in order to solve the nonlinear problem by using a kind of Newton-Raphson algorithm. So here abstractly, we write a nonlinear problem where the operator is y, and we want to solve this nonlinear equation. And the approach will be to generate a sequence of iterates uk that will converge to the solution of the nonlinear problem. And in order to get those iterates, we solve these linearized problems where we solve for the update delta u, and we use the Frechet derivative of y, which is here L, and we on the right-hand side have the residual. And after solving this linear problem, we update the next iterate and then iterate as many times as needed. So using this idea, we have linearized the general form of the nonlinear problem presented before. And now we have this boundary value problem where we solve for the updates to the stress, displacement, and displacement gradient fields. And we have here all the residuals to the equations, and we also linearize the boundary conditions. One thing that I want to point out is that this second equation is an algebraic equation, and that will facilitate part of the implementation for the practical DPG method. But the others are very similar to what we had in the Poisson equation. So on top of those equations, we can add the interface variables that used in the broken ultra-weak formulation for PolyDPG, and those would be the traction and the displacement trace. So these are functions that will be found on the mesh skeleton, and this will satisfy these identities. Very similarly, we will linearize these relationships and obtain the incremental equations for the traction and for the displacement trace. And all of those relationships will be used in the derivation of an ultra-weak variational formulation, similar to the one that we did in the beginning of the talk. So in abstract terms, a broken variational formulation for a linearized problem would look like this. We will find updates for the field variables and for the interface variables in the trial space such that we satisfy the variational equation. And we have contributions from the field variables and the interface variables depending on the value at the iteration k. So this is very important for the linearized context. And now I'm going to present the final broken ultra-weak variational formulation, which is very long, very hard to read, so I won't go into detail. I really want to assure that this is really just an extension of the Poisson problem that we did before. It's not much more complicated than that, but in this case, we are using, instead of the Hilbert spaces, we're using LQ spaces with Q greater than 3. As we mentioned when we were studying the different approaches to the nonlinear problem. So we are posing our problem in the spaces LQ, W, 1Q, and so on. Because the norm of these spaces are stronger than the Hilbert spaces L2 and the family of L2 spaces, then we can show that we can construct the trial to test operator required in the practical DPG method, even for this formulation. And with that, we simply proceed to the discretization of the problem. Here we have a trial space where from which we are drawing the updates to the solution. We have 3 field variables and 2 interface variables that I have introduced before. And we're going to use polynomials of degree p-1 for the field variables, polynomials of degree p for the displacement trace. But in this case, we're going to use continuous traces, because we're restricting our numerical experiments to polyhedral elements with triangular faces. And when we have that case, it is possible to enforce the continuity of the traces throughout the mesh skeleton. So that's the important remark that I wanted to say here. And then also we have the enriched space that we do using the p-enrichment technique. So now let's see an example of this formulation and this method. This is a problem setup that resembles the problem of the elastomeric syntactic foam, although in this case we only work with the matrix material. This will be a hyperelastic material, and the domain is a unit cube with 15 spherical voids that are scattered all over the place with different diameters. And the boundary conditions to this problem are 0 traction on the lateral faces and on the spherical boundaries inside. On the bottom face, we clamp the body, so there's 0 displacement here. And on the top face, we prescribe zero lateral displacement, but we are going to move this face downward. And please see that the boundary conditions, the value is -1 for the vertical component. So that would mean that we are going to flatten completely the body, which is impossible, of course. But what we are going to do is to apply this load by little steps and see how far we can reach within this nonlinear problem. The constitutive law for the material here is based on the Oden model for rubber-like materials. This is a polyconvex coercive constitutive law, and the values of the parameters have been taken from this paper that compares several models for these kind of problems. And also the volumetric term here in the last has this form, which is used in many references for finite elasticity. And we have that the bulk modulus, which is K that enters here, is 10 to the 3. In this case, the units are megapascals. And so for a rubber-like material, a bulk modulus of this size means very slight compressibility. This is a sample of the meshes where we can see that we have a graded meshes with coarse elements on the exterior and fine elements around the spherical voids. So we have put all of our formulation and these problems tab inside a nonlinear solver, which is a modified Newton-Raphson algorithm with load stepping. And for the solution of the linearized problems, we assemble the system in parallel with OpenMP. We factorize and solve the linear systems with the MOMS library. And we can optionally use line search and BFGS updates, which are a kind of quasi-Newton method. And also, I want to show what finite element methods we have used to try to solve our problem. So first, the Petrov-Galerkin method, which is the classical finite element approach, where we use globally continuous shape functions for the trial and test spaces. Then the ultra-weak DPG method using tetrahedral elements with fixed enrichment delta p equals 2, and PolyDPG with continuous traces using variable p enrichment because we have elements with variable number of faces. So it's a small table showing the behavior of the nonlinear solution. I'm showing the type of mesh that we're using, the method. All these problems are just for the lowest order case. I'm showing the degrees of freedom of the total degrees of freedom of the problem, but I'm also showing the size of the linear system. So after applying static condensation, here we see that we reduce the number of total degrees of freedom in DPG from hundreds of thousands to some tens of thousands. So that's very important to have a tractable problem. And I want to draw your attention to this side where I'm showing the size of the load step that we have to take for each of the methods and each of the cases. And for all these four first methods, we have to take very small steps. So this is of the order of 10 to the -3. And even doing so, we can converge in only a very few steps. So finally, the total load that we can apply from the original setup is just nearly 2%. So that's very little. But in the case of PolyDPG with agglomerated elements, we have seen that we can take steps of 2%. So each step we reduce 2% of the height of the body, and we could converge in 26 steps, reaching to 52% of the deformation of the body. And we are very excited to have observed this, but using similar meshes and the same polynomial degree. So pretty much the same conditions, and we have reached a really large deformation. So I'm going to show some solution plots for this last case. So these are wireframes of our mesh. I have decided to do these plots because we can see what happens in the interior of the body. So we can see how the spherical voids deform as we apply more load. And the first image is just the reference configuration. And then I have almost evenly spaced moments of the load application. Here are 16%, 34%, and the final 52%. We can see how the body deforms and how in the end many of the spherical voids have deformed a lot, and how the cubic shape is completely distorted. And so this is very exciting to observe this kind of results. So using that final deform configuration, I can plot the interface variable solutions. In this case, I'm showing on the top row the displacement trace, and on the bottom row the traction. I just want to mention here that we can see how the application of boundary conditions has been reproduced by the method. And for instance, and here on this last image, we can see that on the top face, we have a little negative traction. And here we don't have a traction boundary condition. So this is kind of consistent to the fact that we are compressing the body and the body is feeling a pressure here. These other plots show the interior of the body, the solution in the interior of the body. So in this case, we have piecewise constant for the field variables, but with those field variables that we had in the formulation, we can compute additional quantities. In this case, I'm showing principal stretches and principal stresses, and we have taken the cube and we have made a cut to see what happens inside, and that's why we see a little bit of the spherical voids. And in this particular case, it's interesting to see that there's some kind of a stress concentration in this region, which is a narrow passage between two of the spherical voids. And that is something that is very consistent in the study of mechanics of materials. Those narrow regions produce concentration of stresses. So it's interesting to observe that in our solutions in the inside of the body. And the last plot shows the behavior of the Jacobian of the deformation. We see that the oscillations of the Jacobian is very tiny, and we are very close to 1. And that represents that we are really close to an incompressible setting, being consistent with the properties of the material that we have used. Okay, so after seeing the last results of our ultimate problem, I'm going to tell you some conclusions of the work that has been developed in the dissertation according to the areas of our CSM program. So in area A, we have presented an analysis of variational formulations in fractional sublevel spaces, and we have obtained stability estimates and a priori error estimates. We have also constructed a Fortan operator for polyhedral elements when considering the HP test enrichment option. And in the second part of the dissertation, we have developed a well-posedness analysis for variational formulations of the linearized elastostatics problem. And we have extended the practical DPG for cases of Banach spaces with Q greater than 2. In area B, the main thing to show is that we have developed a hybrid finite element code that can support polyhedral meshes, multiphysics, and higher order approximations. We have incorporated a kind of fast integration for polyhedral elements, which is the homogeneous numerical integration, and that was really helpful for the performance of our method. The interaction of PolyDPG with Voronoi tesselation was possible with the cooperation with Dr. Mohamed Ebeida, and that gave us an extra type of discretization that we could work for the linear problems. And also we have introduced the agglomerated elements where we use graph partition algorithms. And that has given also a nice type of polyhedral discretization where we can enforce continuity of the traces over the mesh skeleton. So that has been very useful as well. And in area C, pretty much consists of the examples that I have shown for linear elasticity and nonlinear elasticity. In linear elasticity, we have used non-conforming discretizations to solve a problem that had high material contrast. And in nonlinear elasticity, we have seen that our method captures a very large deformation of an elastomeric foam when subjected to a compressive load. And apart from that, our results are one of the very first full nonlinear simulations in 3 dimensions made with DPG. So we are very happy to have achieved these nice results in one of the first simulations of this type with our method. So that's the end of the dissertation contents. I have some ideas for future research. For instance, in the implementation of PolyDPG, we would like to support chord boundaries for the polyhedral elements, investigate adaptivity, continue with the investigation on how improve the performance of the method in the integration, but in many other cases as well. For instance, in the solver for agglomerated meshes, and also keep investigating this type of discretization. And on the side of the simulation for nonlinear elasticity problems, we would like to do a theoretical study connecting our development with the nonlinear DPG approaches that have been published by Norbert Hoyer and Karsten Karstensen a couple of years ago. We want to see how they are related. And we want to keep investigating the option for the nonlinear solver to accelerate the convergence, explore more boundary conditions for our ultimate problem to have a more physically appropriate case of a study, and then extend this work to the full simulation of the elastomeric syntactic foam, where we add the second material of the composite material, which are the glass microballoons, and then see how we can contribute to the study of this type of material. All right, so the contents of the dissertation has been included in 2 papers, and of course there is more in more publications that we would like to have in the future, including the second part of the dissertation. But this publication includes the analysis of the method in fractional Sobolev norms, and the first one, it was the case of the 2D method for polygonal elements. And apart from this, I was involved as well in other DPG-related research, working with Siram, Jake Rosek, and Socrates on the simulation of the Maxwell equations for fiber laser amplifiers, where we use the fast integration algorithms that I publish here for all the energy spaces and several DPG formulations. And this other publication where we studied with Jacob the use of B-splines as test functions in DPG. And now that's the end of the technical talk. I want to acknowledge all of you for being here today. I want to really thank my wife, Jana, for everything that she has done for me during these months of hard work and all the love and commitment that she has shown. Thank you to my family that is seeing me today here. My parents, Alicia and Alberto, my hermano Andres, my aunt Judith, all the rest of my family. They have given me a lot of support. I'm very happy to count on them. Thank you especially to my supervisor, Dr. Demkowicz. Thank you for sharing all your experience and wisdom and making us feel like family. It has been an incredible experience working with you. Thank you to all the dissertation committee. They have trusted in the work that I presented to them 2 years ago, and I'm happy that we have reached this point. A special mention to Dr. Bishop that has over these couple of years has given us a few hints on how to direct the research, and that has been really, really useful. Thank you to all the faculty of the Oden Institute and all the staff for all the experience that I had here. They have facilitated and enriched the learning and the living here. Thank you to all my friends from Austin and from elsewhere. For instance, there are many people joining from Colombia and other countries. I appreciate all that. And my colleagues right now in the research group, Stefan, Jacob, Yashi, Eric, Judith, and of course, Jacob, they have been a great help to me. I wouldn't have finished without their help. And to the colleagues that already left, Socrates, Federico, Brendan, Sriram, Ali, thank you to all of them. And to my co-authors and research collaborators, also, I appreciate the collaboration that we have had. Mohammed, Konstantin, and Christos, and all the DPG community, thank you. Thank you so much. And the last mention about the funding that I received, thanks to the Fulbright Commission and the government of Colombia. Thank you to the Oden Institute, to the graduate school, and to Sandia for the LDRD project that we received. Thank you very much. Thank you very much for your attention now, and I'm open to questions.
Okay, thank you, Jaime. The dissertation now is open to questions from the general audience. Please unmute yourself and ask question.
Can I ask a question?
Yeah.
Can I ask a question?
Go ahead, Federico.
So I wasn't clear. So there was the second type of meshes that you mostly use were with these agglomerated tetrahedra that you were mentioning.
Yeah.
What was the reasoning behind the advantage, or what advantages does that type of mesh provide?
Very good question. So let me go back there.
Like what's the underlying reasoning for choosing that type of meshing?
All right. So yeah, it's a very interesting question. One of the things that motivates the use of that kind of meshes is that you can generate a very fine mesh of a body that you are studying, and then instead of using the many thousands of million of elements that you have in that mesh, you can agglomerate. You reduce the size of your problem, but you keep the good representation of the geometry. So you have a good representation of the geometry and a smaller system that you can solve for. So that's one of the ideas behind the use of the agglomerated meshes.
And the agglomeration procedure, you said you were using Metis or something?
I'm using Metis, yes. So I fix the number of.
Why does it choose it? What is Metis doing basically?
All right. So let me go. I think somewhere around here. So with Metis, I can fix the number of tetrahedra per element that I want to have in the final mesh. And also, well, it has a very complete set of functions where I can tell it to optimize the type of agglomeration that I want to have. So what I'm doing in Metis is I'm partitioning the dual graph of the mesh, and that is helpful for partitioning meshes. So pretty much I use Metis because that will give me a general tool for any kind of NetGen mesh that I input, and will give me the satisfaction of the number of tetrahedra per polyhedral cell. So,
okay, so you're keeping the number of roughly the number of tetrahedra.
Yeah, roughly, yes. It varies plus or minus one usually, but
okay,
most of them are satisfy the number that I want to use. Yes, thank you.
Any more questions?
Yeah. Hi, Jaime, this is Norbert.
Hi.
So when you consider the discontinuous trace approximation, so I have a question that might not be relevant for practical issues, but it might be interesting theoretically. Do you have control of this constant that depends on epsilon? So you might want to consider epsilon being dependent on h to get a logarithm or something like that. Have you thought about that?
I don't believe we have that control. Yes, we explored the getting that logarithmic term, but yes, we don't have the control of that constant depending. We will observe the blow up. Yes, we explored that possibility when doing the paper, but it's not the case as you said when you can fix the value of h or of epsilon and obtain that logarithmic estimate. Yeah. I don't think we can.
Usually it's just scaling arguments, things like that, right? So, but
yes,
probably there are issues I don't see. Yeah, so I know.
Yeah, there was a lot of scaling arguments and controlling all the different fractional sublet norms that there exist. We wanted to have some kind of uniform equivalent between all of them, but at some point, we cannot control everything, and we cannot do that.
All right, thank you.
Thank you.
So, Norbert, if I may add, we control the power with which it blows up, but we don't control the constant in front of it.
Yeah, well, probably you can discuss it later. It's hard to imagine that you can control the power, but then you don't have access to the constant. But usually you have the power and the scaling, and that's it. But okay, so we can discuss that.
Right.
Different occasion. Thanks.
Thank you.
A quick question, if I may.
So it is clear you went for a non-conforming method, but did I get it right at some point? There are some cases where conformity can't be established.
Yes, I think
for the traces when you're trying to discretize the traces.
That's right. That's right. So, unfortunately, I'm stepping on this slide. So when I use meshes that are, for instance, of only tetrahedra or the agglomerated tetrahedra, all the faces in the mesh will be triangles. And when we have triangles, we know how to enforce the continuity of the basis functions. Because by knowing the orientation of the edges and the vertices that are shared by the different faces, we can construct a globally continuous basis. And we have chosen to use that in the nonlinear problem because we believe that using discontinuous deformation for the traces would be a little non-physical, and we prefer to enforce that the faces move together with that continuity enforcement.
Okay, thanks.
Did I respond?
Any more questions?
I have a question. I just late at this.
No worries.
Jaime, I'm just have a doubt. I arrived too late and I cannot question about the specific question I have.
Yes.
But I want to understand what kind of relation are you looking for in the computational power you will use to optimize the way you choose to solve the specific problem. I don't know. I'm making myself clear in my question.
Not so much. So regarding the implementation, where we can optimize the performance, or
no, about the for example, I have made some in research about something not close that your research, but very related, but the power of computer you need to achieve some level of optimization. So my specific doubt is, are you engaging also taking in account the power of computer, you need modifying a specific, I mean, like how powerful you can use that in the name of computational power. I mean,
I think more or less, I think what you want to ask. So I get that for larger problems than the one that I have shown today, it would be really important to scale the algorithms that I have used, and hopefully we can use some of the technologies that we have available here at the university, the supercomputers, where we can use several compute nodes with MPI. Actually, we're close to getting there, thanks to one of our colleagues, Stefan, that has developed an MPI code. And then we can work in parallel in several compute nodes, and we will solve very quickly each of the linearized problems. And for the nonlinear problem, of course, that will take some time to do, but that will be necessary when attempting very large problems. So what I showed today was a limited size of the problem, and I have more or less improved the performance of the method for linear problems, but when addressing nonlinear problems, since we have to solve so many times the linear problem, then I couldn't solve very big problems. We will need to scale the code and work in MPI to address models with more complexity than the one I showed. But I think we can scale thanks to the code that Stefan has done. Very soon, we can do something like that.
Thank you so much.
Yeah.
Okay, if there are no more questions, then I would like now to thank the general audience for wonderful participation.
Thank you.
And ask everybody to leave the Zoom meeting except for the committee members.
Okay. Yeah, let me stop the recording.